evolved, that was not progressive. So every time something new came, again you have to plan new. Maybe old rules became obsolete or not no more functional because technology has changed, and it used to go on going. So it used to take forever. That's why there is very little evidence that the companies have implemented on a very large scale in a very complex environments like aerospace or medical. There are some companies that have done that, but because the cost and the complexity involved and chances is very less. Very big companies have only done that till late. Now, once after this Transformers paper came from Google and ChatGPT and all this progress, after the computing limits have been broken, so AI has become a reality. The deep learning technologies, where the machine will learn itself, or machine learning, whatever is the way. We show them some examples which are characterized. Okay, this is good, this is bad, this is not acceptable, this is acceptable, this is partially acceptable, so that it learns the patterns. Once it learns the patterns, so it keeps improving itself. It keeps making itself smarter, like a regular way. So this data model is trained. You feed all that photos and then get the output. This is one of the ways in which artificial intelligence can be used from the optical perspective in inspection. The next thing is where optical fails. So we go for X-ray defect. X-ray. So when if you have seen a typical X-ray, what it shows? It shows your bones. Why bones? Because your bones are mostly metallic. So and our electronics also involves what? Copper, aluminium, gold, right? So these are all metals. If you and alloys of like solder alloys are also metals. If we see them through a X-ray, we will find that other things are either translucent or they are not at all visible in the X-ray. So we are able to focus on our interest points. Like here, if you can see some images, here the X-ray has been taken off a device which is wire bonded, and here you can see there is an opening here. Similarly, here a device has been soldered and it is below the PCB, and we cannot see through eyes, but X-ray, because X-ray can pass through it. So we have seen that there is an X-ray solder, uh, there is insufficient reflow, there is a short, there is a void, there is a misalignment. So what it basically, how it basically helps is where optical or our eyes cannot do, because we need a line of sight. X-ray helps, not to a 100% extent, so that if we say we can say that optical inspection has covered this much, and if we go by X-ray, then we are 100% sure that the circuit is fine. But okay, up to an acceptable level. So these two techniques, optical inspection, X-ray, have been used extensively till date, and they are still being used. And in medical industry, what I have found is AI-based tools have come. It can analyze the patient's X-ray and tell the doctor. Then doctor can take decisions. He can refuse or take decisions. That is done faster. Same way we can also do for the electronics. Next is failure prediction. Uh, we keep generating data. As I told you, there are thousands of joints, nearly 1 lakh joints in a satellite of all the circuits of satellite. Ever since the design starts till the spacecraft is launched until the lifetime is completed, we keep generating a lot of data. But till now, we do not have any way to make sense of the data. Okay, data analysis tools were there, but they were still dependent on the skill of the person who is using that data. There was no concurrency, there was no consistency between person to person, and we had to dedicate so many resources to find the relationship between a certain factor to a certain output. And it was not every time very linear or very single polar. It was very multivariate. So if you have seen a fishbone diagram, you can find that for everything there are fins that are associated. Similarly, here what will happen is, let me take this as an example. Let's say there is a satellite that is 2 years in orbit. Now, 2 years in orbit means satellite would have much more been designed before 2 years. Then would have taken some realization time. Then all this data means it would have gone through all the processes and steps. All this data has been captured. So what happens is there is a model that is specifically trained for this. We keep giving all this data. So let's take an example of a transistor. A transistor is going on a PCB. That PCB is going in a subsystem, that subsystem going in a satellite, and the satellite is being launched. So we track the transistor. We have seen the history of the transistor that okay, if it experiences thousands of temperature cycles of this temperature swings for these many hours at this functional level, what we found that the functionality of the transistor has gone down. Let's say degradation has started. So, or let's say the temperature is not this much. If the temperature range is less, if the timing is less, if the functionality percentage is less, the life is more. So this way we know that our predicted lifetime of a thing, the component is this under these conditions. So previously, what we used to do, we used to draw a simple model, which to try or design a simple model for each and every component, which are not necessarily true, which are most of the time it was not true. So each model, each component can be modeled in various submodels. If you can see, those submodels can be analyzed, and based on analysis of those submodels, we can arrive at a figure, which is more or less accurate based on the historical data. What we have fed to the model. So it will analyze the temperature cycles that will undergo, the vibrations that will happen in the satellite, the operational hours, all the radiation activity, and everything, whatever sensors is sent to the Earth station. Now, the AI says there is a warning because you have subjected this particular module or particular circuit to these many extreme harsh conditions. It will fail in 2 weeks, 3 weeks, 1 month. So next step it will suggest, okay, what to do if you want this component to work more, you reduce the temperature limits. You turn on something so that the temperature goes out, or what you do, you reduce the working hours. You take the load from that particular component to the other component, because in satellite follow the concept of mean and redundant. There's nothing in satellite that goes usually, typically, that is the single point failure. You always keep a backup. We call it mean and redundant. So it will ask to shift it to redundant so that mean gets some stress relief, or if you have backup, or if you have some other backup. So this way, not only it helps us predict what will be the failure, what can be the failure, it will also tell us what is the remaining useful life. This way, we can even extend the life from the design life. If possible, so maybe the data can help us to find it. Okay, we planned the design life as per these conditions, but if we switch these conditions, that AI insights will tell that okay, we can increase the life. Right? And the next one is very important and it's a very cool one, the digital twin. So, what is a digital twin first? So, till now, we all know that we have been designing electrical circuits. We have transistors, diodes, and everything, and we have equations. So, if we see what are those equations actually, there are things but just models of the actual physical hardware. Correct? We have V is equals to IR for a register. So this equation is what? It represents a relationship. It's a model. Similarly, there are in network theory we have Z parameters, H parameters, and everything. So what these actually do? They help us model it, right? So these modeling, if we take to a very large level, from the very component level to the very macro level, from chip we have models, and chip to package model, package to PCB, PCB to subsystem, and subsystem to satellite. If we combine all these models, we have a completely functional satellite that is working inside a computer. So how what? So it's a virtual copy. There is a satellite that is actually in the orbit, and there's a virtual copy that is exactly same as the satellite which is in orbit, and it is completely mirroring. How it mirrors is real satellite temperature or some sensor data. It sends to the Earth station. That sensor data is fed to the digital twin. To the digital twin, because it knows that if these parameters come to the satellite, this happens. So the digital twin also shows similar impacts. So the manifestation of those environmental conditions or those factors will be seen in the digital twin. Now AI will compare both the versions, and the changes will not be a single variable here and there. The changes will be from the micro level to the macro level. To track those changes through hard code or any other way is infeasible. This is where the AI, and because it has big data crunching capability, it comes. So it will find each and every factor, it will isolate each and every factor where the difference is. Now it will improve the digital twin. So after some time, what happens is the way satellite functions and the way digital twin functions will be nearly identical, and we will be able to guess what is going to happen because we can subject the digital twin to whatever factors we want because it is a virtual copy. So we can to anomaly detection. Now, we will subject the digital twin to extreme ranges to find where anomaly can happen, because we know that, let's say, after 1 week the satellite is going to a zone where the radiation will be too hard. So 1 week prior, we'll have the data, we'll have the information. Okay, digital twin has done like this, so these are the things that will get suffered. Will either turn off, reduce their voltages, current, power, whatever it is. Live prediction. Digital twin is complete copy of that. So here only it will show that, okay, because you are subjecting this particular subsystem to these things, this will go back. Life will or life or failure prediction, they are just inversions of each other. And mission planning. Although when mission planning goes, there are things that they have to decide from Earth based on the sensor data that we receive, and then we do calculations, and then we send to the satellite to make its course correction, change the orbit, change orientation, alignment, and all the things. But here, what will happen is we will simulate all the situations with the digital twin, whatever is possible in the next 1 week, 1 month, 2 months, 1 year after that. And we have all the necessary steps that will be required. And we can feed in advance to the satellite, okay, do this when this comes. The satellite has very limited things. This is a very useful thing. They are being used in industry, but not in aerospace till now because of the complexities involved, and there are some other reliability concerns. But okay, this offers a very useful application, and it offers a very huge, what to say, huge computational benefit you will get, because once this comes into picture and people are working on this, it seems that NASA has already done it, and since 2010 they have been actively using it. But there's a very little data on how much accurate and what is the reliability of those twins. But yes, people are doing it, and we also will do in the future. Next thing is, let's go back to the shoulder joint example. 1 lakh joints. So those joints, they are done not all the soldering in batches to a machine. The machine works on certain parameters like speed, process temperature, pressure ranges, and all those things. Then there is a yield. Let's say we pass 100 PCBs in an hour, so we receive 99 PCBs after soldering, which are acceptable. So that's called yield. Inspection time. So because inspection is also part of manufacturing, because until unless that's inspected and cleared, we don't say it is completed, manufactured for the next process. We have we'll have all these parameters. We could optimize. We could learn full patterns, because till now, once a pattern is certified or qualified, we go to the same, and we usually don't try to deviate from that. But once this data is there, we will be able to understand what happens if we deviate from it. So this is one example that is very actively being used in industry and other spaces also. Now, if AI is so good, applications are there like automatic optical inspection is already in there in industry. Your smartphones, if I give you the very best example, your smartphones, like many of the manufacturing companies, your laptops, especially in China where they are made in the third party contractors facility. In the same facility, you will find that one line goes for the HP, other line goes for the Lenovo. They have this automatic optical inspection systems where PCBs are inspected in hundreds per hour, if not thousands. Actual defect detection systems are also working very fine. They're very good, especially in medical industry. They are doing like anything. In normal consumer electronics, also they are doing like anything. This the next thing is manufacturing optimizations have happened at a scale we have never seen earlier, because previously it used to take years to realize, okay, this is the pattern, but now we are doing in minutes or in hours. Various are better, the useful life, everything is going on. But still, why is that AI is so great, and why it's everywhere? So there are some challenges that is stopping us to put it everywhere. We only know ChatGPT, Gemini, they can generate code, they can generate text, they can generate images. Fine, because this is what we have seen. There are some challenges. So number one is training data. So when it comes to satellites or aerospace in general, we have very limited training data. As I give you the example of smartphone manufacturer, iPhone or Apple itself ships nearly more than 1 million iPhones, and combined with Samsung, if you go, I think it would be 3 to 4 million per year. And each smartphone contains at least five PCBs inside it, minimum. So you can see the how much quantum of data they have to train the model. But in satellites, we don't have that luxury. We can realize 8, 10, maximum 12 missions. We neither have the manpower nor that much capability nor the infrastructure, and it is very difficult to scale that. It will not be justifiable to scale it to that level that okay, we want to generate data for 50 satellites, 100 satellites in a year. So it's not scalable as of now. How do you train if you have no data? So the way is synthetic data. So instead of waiting for real failures, we create fake ones. How we create? So there is something called physics simulations. If somebody would have used COMSOL or tools like Ansys and this Cadence, there are some tools that helps you see what happens that if you put certain heat on that particular component, to put certain force on that component, if you give some radiation to that component, if some ionic activity happens. So these are a lot of physics based models that are used, that there are certain tools for that. You simulate that data and we see, okay, this happens, so this happens. So this gives us some data of the failure. So we try to simulate what are the failure points that are fairly accurate because those models have been working for years in those simulation tools and they have given kind of good real life, what to say, uh, not with very much deviations. So we run computer models to guess and see what happens during stress. Digital tools, as I explained earlier, but that also requires data. Image augmentation, because here our focus is on inspection of soldering joints. So images, let's say a PCB is slightly tilted when it comes to the camera. So what will the model do? It won't be able to find because it has not been trained on that. So all those conditions will make different images for the same image. We'll rotate it, flip it, modify the photos, change the background, change the transparency and everything. So that for one single image, we are able to generate n number of images which are useful for us. Then there are CAD models. Now CAD models are also very good because each CAD design can give you n number of perspectives the way you want. You can rotate it in the way you can go inside and all those things. So if we capture each and every perspective, whatever is important from us from the design file or the CAD model, then we have the data instead of subjecting the actual model. So this is the problem number one, and this is one of the many solutions that we can use in our like satellite domain. It's not that it's everywhere are using, but in satellite domain it can be useful. The next problem that is the why problem or the explainability and trust. Few years back, Anthropic released a paper saying that we don't know how it is working. Okay, the conclusion or the summary of that paper was they don't know how their AI tool, their Claude is working. So they are feeding some prompt, they're getting some output, and they don't know how that input is related to the output. There is a complete black box. Missions like satellites or even in medical. I'll tell you very simple example. Quality says AI has rejected this joint, and somebody asks why. But you say this AI says it is 99% defect, but we need to know why. Why AI says that it is there? What are the criteria on which it says? How will you explain that certain thing is acceptable, certain things rejected? Because that traceability is very important. Once something happens or even something goes slightly off the course, there is the concept of explainable AI that has gained some trend in last few years. Once this black box thing came into picture and people were able to see that okay, this is not good because we don't know how it is doing, and if we don't know the process how it is doing, then predicting the output of that process is very difficult. And if that's the case, then it cannot be given for some mission critical things. So how explainable AI helps is it breaks down why sir it has done the way it has done. If you write some code in the thinking model of anything, it will say it is thinking like this. If somebody would have used perplexity, says thinking the way first step is the second, but still that is not convincing. So what we want actually is if it something says something is accept or reject, it should say why it is acceptable. What are the parameters that it has met? How it has done. Similarly, if it says it has rejected, let's say it has rejected because of a crack. So it should highlight the crack with a red box. Let's say there is a suspicious solder region that okay whether the solder is done or not, it should point because it cannot take a decision. It doesn't have the data to analyze on a suspicious case. If there is a void, it should measure the void because 100% void cannot be taken out. There will be some void after a solder. If some abnormal Excel features are there, that is beyond its beyond its trained data, it should not hallucinate. It should not just generate some conclusion just for the sake of conclusion. That's what's happening with the current tools, right? So this is the second problem, and this explainable AI may give some solutions in the future. That's what. Third one is power and computing. If you are in touch with news, you might have heard that Facebook is trying to revive a old nuclear power plant to power its data center, its computing center, basically for its AI projects. Why? So each AI center has terabytes of RAM memory, hundreds, if not thousands, of GPU clusters, associated heat machinery, infrastructure, and everything. So the scale is in megawatts. It's not even kilowatt. It's megawatts, and sometimes now it is going up to gigawatts. But satellites have only few kilowatts, 2, 3, 5, 10 max. That's it. Memory, let's say even if the best of what we have, we can maximum we can figure. Let's say just assume take some 1 or 2 TB at the max, not more than that. Heat. Here on data centers, we have dedicated heat cooling system that keep running continuously 24/7 at very high efficiency takeout rate. They're all conduction convection based. We don't have that luxury there. Now the example is a high-end GPU like H100 or H200 of that. I don't know what that called NVIDIA. It has uses of 300 to 500 watts, maybe sometimes more. We don't know. Satellites have a limited power, so it becomes infeasible to put to have to assume that satellites will have that computing capability. So the answer is HAI. HAI, why it came into picture is we don't want everything to happen at a single dedicated central location, every decision, everything to happen. And there were concerns regarding data and everything, and also letting the thing that every data has to be transmitted and to take its time. So why not take the decision at the place of actuation? So very small models, not billions of parameters, very few, let's say a million parameters, which are fairly accurate, okay, and which have been trained on a sufficiently good data, and they are being fed to the satellites. The satellites computing power per watt is important, per MB is important. So all those things, if we take into consideration, we should find the model, we should tune the model so that it works there for the life of a satellite. Maybe it's not that it should work every time, but it should work, let's say, for a satellite duration of 15 years, it works half of the time, let's say. Every half an hour it works, or every 15 minutes it works, so that it saves some time, it saves some power, it saves some memory. So the simple analogy is that those data centers are like smart supercomputers. But what we have in our hands is a smartphone. It meets our requirement. It's very limited. It does not meet those computing requirements or the performance, but it meets our requirements. Similarly, in the case of satellites. Another thing is next that defines this domain is qualification certification. Everything that goes into a space has to go or has to pass all the reliability parameters, not only on the product itself, but in the process also. And that qualification certification requires time, money, effort, and it has to pass through many standards. Now, component goes to vibration testing, thermal, radiation, qualification, everything. For these things, qualification criteria have been already defined in the aerospace standards, and they are working very fine till date. And there is no doubt on those things. You cannot say that okay, this standard is lagging in this thing. Okay, some minor improvements happen here and there with every revision, but let's overall broadly it is still the same. Those qualification parameters are still working very good throughout the world. But how to certify AI? AI is just a model trained on some data, okay, and it gives some data. And we also don't know how it gives some data. How is that model working? That thing is happening. AI these models have to be changed that the system can work, have to be retrained, have to be configured. What happens if we do like that? Because there's a very simple there's the concept of men machine material method 4M. If any of these changes in space, we go for qualification certification. Men means if some person who was doing the job is qualified, he changes or he happens something. qualification. Material. Let's say you're using solder A, that was qualified. We want to move to solder B, qualification. Method. We were using the reflow process. Now you want to go for advanced something. Again, qualification. This material. Sorry, method,
Mm.
material, machine. Let's say you're using a machine X. Now you want to use the machine Y because of some issue. Again, you go for qualification. But in AI, how will you do like that? Because all these things, these four M's happen very rarely. But AI changes its parameters daily if you train it, right? So the solution is AI assurance frameworks. So we need to define a framework standard such that how AI should behave is how it should be first trained, what type of data should be captured, and after training, what are the minimum accepted criteria that it should perform such that it becomes spaceworthy or site-worthy. We need to prove that whatever AI is doing, it's correct. We have to validate it. It's not only verify, we have to validate it. Like we have ISO, we should have certification standards. Till now, they are not there in the space as of now. There's no industry that has any certification or qualification standard for AI. Audit risk, it's a human error. Definitely, because a human made error, same error is being learned by AI. Operator bias. Let's say something appears shining to me and something appears less shiny to somebody else. So for me, it will be good. For him, it will not be good. So same data labeled by two different people will be given different category because we had some bias. So these are the problems that are the data quality.
निकाला ओके.
Is that quality? AI systems for optical or even X-ray requires cameras, hardware, computing, software, field engineers, testing. It requires some millions of dollars to do all these things. But whether it is justifiable, if you see the long-term savings that you will get by preventing one satellite failure or a delay, should pay for everything. One space mission costs nearly $500 million. So here we are spending just 1 billion. So if I go by the calculation, it's not even zero point 0.1 or 0.5%. And if you just spread that calculation for let's say 10 years, 15 years, 20 years, becomes even less. So although it is costly, there is the initial implementation cost, setup cost, and everything. But if we see the spread, the way it is done in the balance sheet of any company, like the depreciation for any equipment. Similarly, if we spread that cost, this capital cost, then we'll be able to realize how important it is and how much cost effective it is if we are able to do it in the correct way. So it will reduce inspection time, man hours are reduced, cost is reduced. Manufacturing defects, definitely the earlier you catch, the much cheaper it is. Rework cost, because rework also requires some money. Mission risk, most dangerous of all. That mission risk will be minimized. Till now, we are minimizing it through manual impact. Now there will be the system that will be continuously working. The chances will be less, and yes, because it will be reduced, the chances that our missions will fail or not meet our objectives will be very, very less, so that money will be justified. So the cost spread has to be taken into consideration. Next is human expertise. Now, even after everything is there, AI is very good on repetitive and consistent things. But what happens next? Something unusual comes. Then there AI will either hallucinate, which it should not do. Here case, it should simply say, "Oh, okay, I don't know. Let's bring a human into picture." Now there are some failures that have never occurred before. Now it is happening. AI should say, "Okay, I don't know. Please come." Similarly, mission-specific requirements which are not trained to the digital twin. Now the digital twin needs that, so a human has to come into picture. And now there will be a trade-off between competing goals. Like, okay, the system says that computation requirement is it should work continuously for 10 hours on onboard satellite. But there is a sensor that is giving an alarm that if you work for more than 6 hours, then it will fail. So how are you should do, because you need 10 hours. There has to be some trade-off. That decision cannot be taken by AI. So human still has to be there. That's still a problem. We cannot completely. So I don't count it as a problem. Actually, I count it as an opportunity. AI will not replace experienced people, the people who have knowledge of their domain. If we see it as our competitor, then we will not be able to take the full advantage as other people are selling. Okay, it should be AI plus engineers that should work such that not only AI progresses, but we also progress. Like previously, I will give you a very simple thing. Previously, if you wanted to code, The only way you had is you have to learn coding. But now, even you need to learn code to write a very good, to make a design and develop a very good software. But to get some hands on it, to make a general thing, you don't need to learn code. You can write prompts and AI will help you. So it's not that it has replaced developers or coders. So it has been most extensively used in industry in that way. That's why I'm giving you this example. Similarly, if you are working, let's say if you are an electronics engineer, computer science engineer, electrical engineer, it's not that it will replace you, it will help you. Previously, if you are taking n number of, let's say, 10 hours to design a circuit, maybe it will help you doing in 1 hour. So the scale of work will only increase, the output will only increase. So here, it's not a problem, it's an opportunity for all of us to go ahead such that if we take it as a competitor, then let us face it, AI is going to stay, and please be ready for this. With this, I would like to end. Thank you. Over to you, ma'am.
Moving on into the lab, we just need to get into a motivational background. Why emerging tech? Are we witnessing some revolution? So already we have been honored to hear from Professor J. Ram Kumar sir from IIT Kanpur, a very elaborative and insightful session on Industry 4.0 and Industry 5.0. So just an overview. See, technology is something which, by the virtue of application of scientific principles, it makes problems easier. It finds solution to problems, and the application of science and scientific principles comes out as technological solution. We are using mobile phone without bothering to learn about embedded electronics, without bothering to learn about the chips, integrated circuits, and VLSI. But mobile phone is inevitable. We cannot, uh, uh, survive, or we cannot live comfortably without using smartphones. And similarly with internet, and similarly today, AI is also becoming a part of our, uh, you know, lifestyle. It is becoming a part of our lifestyle. It is so these the technological interventions, the technological advancements which we are witnessing today has been uh, an outcome of an evolution. This evolution is displayed over here uh, uh, on the slide. So in 1780s, we experienced a huge transition in industry by the advent of power of steam, bhap ki takat. So steam was produced by boiling large tons of water through using the energy as a coal, energy from combustion of coal. And this power of steam led to this is the scientific principle: steam and Pascal's law and pressure, thermodynamics. This is science, and the technology is the steam engine. Steam engines resulted into major mechanization, and the industry, specifically textile mills. See, in ages and in different eras, we have witnessed certain specific domain of industry undergoing some revolution. For example, today we are witnessing a revolution in information and communication technologies. ICT is leading the world. So in 1780s, textile mills and cloth making industries were on peak. So textile mills experienced mechanization by the advent of steam power. Similarly, 100 years forward, we experienced a revolution in industry because of advent of electricity. So see, we are using light bulbs, we are using electrical appliances. Everyone, every literate or illiterate person has to. We are all familiar about electricity, vidyut, electrical appliances, but we only a few of us are well versed with the electrostatic principles, the current, electricity, so all the science which we deal with. So this is known as the revolution, that the technological solution becomes a part of our life. We cannot avoid the using those technological applications without bothering into entering the details of the scientific principles which is at the back end. In 1970s, see, electronics and computers were invented, and large applications of electronics, semiconductor industry was emerging. So the energy source was electricity, and the transformation was directly reflected in automation. So we had CNC machines, industrial robots, and these revolutions came into picture. The traditional manufacturing was converted into transformed into semi-automated manufacturing by the advent of industrial robots and CNC machines. So 1970s experienced the revolution, and 2011 onwards, 2011 onwards, we are witnessing a humongous application of a bunch of emerging technologies. These technologies can be named as sensor technology, communication technologies like 4G and 5G, Internet of Things, data revolution, we can say, big data, data analytics, artificial intelligence, robotics, so green energy, cloud computing, blockchains, cyber physical systems, Wi-Fi, broadbands. So these set of technologies in many applications used collectively. There are several applications we can think of wherein I've named 7, 8 technologies or 10 technologies. We are using 5 to 6 technologies at the same time. For example, if you go in a modern diagnostic lab, which is a facility of some hospitals. So if you go for a modern diagnostic lab for a test like MRI, CT scan, we can see cloud computing, we can see robotics. Okay, robotic end effectors are used to carry the plates and capture the images from the patient's uh, organs or parts which have to be scanned. So robotics is there, internet is there, cloud computing is there, data has been data received in the tests, data captured in those tests is saved on some cloud, uh, from where that platform doctors or different stakeholders of the medical infrastructure may retrieve and process those data. We are see many hospitals like AIMS, even the medical colleges, the state medical colleges, Tata Memorial Research Center. We are all working on e-medicine. Electronic medical reports are there. So doctor on several clicks can retrieve all the files, all the details of the patients which have been previously evaluated. So this is all a result of a collection of these collective technologies. So this revolution is known as fourth industrial revolution or industry 4.0. One of major applications, an industry which has transformed a lot through fourth industrial revolution is manufacturing sector. And one of these technologies is additive manufacturing or 3D printing. This 3D printing, so this is known as people. Planet, we are all very much aware about the sustainability approaches, uh, considering climate, environment, conservation practices, use of natural resources, judicious use of natural resources. This is all the planet vertical, and profit means uh, adaptation and implementation of these technologies should now what the part will be created, what shall be the shape, what would be the features. It has all to be decided in computer by using software technologies known as computer aided design, CAD. So CAD is a platform. There are different tools like SolidWorks, Fusion 360, CATIA, wherein these 3D models are designed, and based upon those 3D models, uh, a digital file is created. Digital file carries the information on the path and how the material has to be deposited in what pattern. So here is a very simple representation of traditional manufacturing versus additive manufacturing. Traditional manufacturing, previously we were using metal cutting, and even with technology we used CNC machines that is also doing metal cutting operations. So see, we have a block and there is a finished part. So we have to create certain holes and remove material from the block. Then only this part can be created. This will result into waste generation. While if the same part is to be produced by additive manufacturing, the extruder will deposit materials only where it is desired. If there is a hole, material will not be deposited in the hole. We can optimize this path of design, this path of this entire formula of production. We can optimize and we can generate in computer softwares. While slicing the files, while slicing the models, we can optimize all these parameters so that zero or very less waste is generated, because there is no scope of waste generation, because the material is deposited only where it is desired as per the design. Several examples and applications: turbine blades, aerospace brackets, dental aligners, medical implants. We'll see certain these prototypes printed parts in our lab. Meanwhile, I'll request our coordinators and Dr. Sanjeev Sharma sir to kindly inform aligners. We need to take X-ray of the dental, jaw line and dental sockets. Features of the jaw and the gums. So if there is any deviation, that may result into mismatch. And if the patient has to compromise with a mismatched, wrongly developed dental aligners, it may result into several um, long-term diseases or chronic diseases problems because of this deviation, because of unhygienic uh, conditions in the mouth which will develop over time. It is also a result of oral cancers. So precision here again is very important, and we cannot compromise with the precise designs. In this case, in these examples, 3D printing is the only solution. Why? Because we can, by reverse engineering, we can create the exact CAD models of the need. We can create the designs, the computer-aided design models, and based upon computer-aided design models, our printer will deposit material exactly following the design. If there is any error in the design, that will be replicated in the product. If there is no error in the design, so we can design things, we can simulate, we can model, we can test even the before manufacturing the products. This is the beauty of this technology. If before manufacturing the product does not exist, and we have tested. We have tested the design, we have tested the prototypes, we have by techniques like simulation. Think about the stents, the medical implants which are placed by massive surgeries, which are placed artificial parts and implants which are placed in the body, like graft, valve, and cardiac surgeries.